Welcome on another tutorial on digital modulation. In a couple of videos that I've already done, we have already talked about analog modulation, and digital modulation, it's no different than analog modulation. So we will talk about it. Everything is the same, but just that here we are dealing with discrete data, or let's say digital, which means that we are going to use 0 and 1s. That's what I mean. So basically, let's dive into that digital modulation. So first of all, let's talk about why modulation, or let's define modulation. As I defined modulation in my previous videos about analog modulation, modulation is the process of changing the phase, the frequency, and the amplitude of a carrier signal with respect to the change in the phase, amplitude, and the frequency of a message signal. The same thing applies to digital modulation, which has the same definition. So let's talk about why modulation. Before diving into how, let's first understand why we need modulation, right? So we live in a digital world right now with information represented as a sequence of zeros and ones, right? With information represented as what? Zeros and ones, right? However, directly transmitting these digital signals will face some practical challenges. So let's talk about some of the practical challenges that I'm talking about here. So some of the practical challenges include a limited range. When I say a limited range, digital signals have low power and are therefore prone to attenuation over a long distance, right? That's what I mean by digital limited range. So let's also talk about the interference. So as I said earlier in my previous video in analog modulation, these digital signals are also susceptible to noise and interference from other electrical sources. So modulating it will help her to be immune in all these interferences. And let's talk about the third one, which is the spectrum. Let's see, the spectrum efficiency. So basically, an unmodulated digital signals occupy a very wide bandwidth, right? So making, if you want to make it efficient, or making an efficient use of the limited radio spectrum challenging, you have to actually employ modulation. So that's another reason why we do modulation. So basically, modulation overcomes this limitation by actually imposing the digital information onto a carrier signal, right? So basically, if the digital information is 101, we impose this digital information onto a carrier signal, right? Carrier signal. So this carrier signal typically has a higher frequency, like that's in analog modulation, it has a higher frequency. So let's talk about some advantage of doing modulation, some advantages doing digital modulation. So as we have already discussed here, we were saying that with the modulation, we will face these challenges, and this is not all. So when we are going to talk about advantages, it means that the opposite of these ones is definitely going to give us the advantages of modulation of the digital signal. So basically, when you modulate the digital signal, you increase the range. That is, the higher frequency carrier travels further with less attenuation, right? So if you modulate it, it will travel further with less attenuation. So the next one that I would like to talk about is like improved noise immunity, right? That there will be no interferences. So the carrier's stronger signal makes it less susceptible to noise, right? Because the carrier has a stronger signal, it will be very difficult to make it susceptible to noise. Therefore, we can say that it's improved noise immunity. And then the last one that I would like to talk about here is the same thing, which is the spectral efficiency. So modulating the carrier allows for efficient packing of multiple data streams within a limited bandwidth, right? You don't have to use plenty bandwidth when you do modulation. But without modulation, you make use of a lot of bandwidth, very wide bandwidth, right? So basically, what I would say is that just like analog modulation, we also have the three types of digital modulation, which is the same scenario, which is amplitude, phase, and then frequency. But in this digital modulation, instead of calling it amplitude modulation, we call it amplitude shift key, which is ASK. And some people also call it binary amplitude shift key, which is BASK. The next one that I would like to talk about, it's also the frequency, right? It's the same as the analog modeling, just that the name, the way we call it is different. So basically the frequency is frequency shift key, or key, you can decide to, which is FSK, or BFSK, which is binary frequency shift key. And then the last one that I would like us to talk about is the phase shift key. Even though we talk about different aspects, the other ones that are present and can be used for modulation, we talk about it, but for now, this is the three main types of digital modulation that we are going to consider. And the last one is phase modulation, or let's say phase shift key, which is PSK, or binary PSK. So these are the three types of digital modulation that we are going to consider after everything. So let me talk a little bit about these types of digital modulation, and after this video we will take them one after the other and then analyze them, do mathematical analysis, including generation and detection. So talking about the amplitude shift key, here the amplitude of the carrier signal is actually varied according to the digital data, right? So if the digital data is 1, right, if you are varying the amplitude, you see the change in the amplitude of the carrier signal. If the digital signal is 0, you see the change in amplitude in the carrier signal as well. So basically, I will show you when we take them one after the other some diagrams that I need to know. So the second one is also the frequency shift key. For this one, the frequency of the carrier signal changes with respect to the change of the amplitude of the message signal or the data, right? As I said, the frequency of the carrier is actually shifted to represent the digital data, right? And then the last one is the phase shift key, which is the basis of which the carrier signal is actually encoded, or like is used to encode the digital data, right? So in this way, the phase changes with respect to the change in amplitude of the message signal, right? Which is the digital data that we are putting in. So basically, we will take them one after the other and talk about them in my next video. So let's kind of look at something here. In each of these type of digital modulation that we will consider, we will talk about the bandwidth aspect, the bit rate, and other stuff as well. And then before we go ahead and end this video, let's try and know some various application for digital modulation. So someone can ask, what are the various use of maybe digital modulation? Even though we have already discussed some advantage, which should kind of give you some hints about the application or the various use of digital modulation. But not to waste much time, let's kind of look at few of them here. Now, for digital modulation, they are mostly used in wireless communication. And these wireless communication includes cell phones, Wi-Fi, and Bluetooth devices. And these devices, they all rely on digital modulation to transmit and receive data wirelessly. And the next one I would like us to talk about is the satellite communication. Satellites are digitally modulated to send and receive data over a very long distance. So this is also one crucial application of digital modulation. The last one that I would like us to talk about is also broadcasting. So basically, if I say broadcasting, I mean the radio and the television broadcasting. And these radio and television broadcasting utilizes digital modulation techniques for signal transmission, and it's popular, right? So as we talk about the amplitude shift key, the frequency shift key, and then the phase shift key, you get to know more about these types of digital modulation, and you appreciate them. So thank you for watching, and see you in my next video.